know why it hid that. Anyway, thanks for coming and welcome to the next GPU talk in the stat department here at Iowa State. So today I'm going to be talking about the CUBLAS and CULA libraries. They're linear algebra libraries. Rather than invent your own routines for matrix algebra, you'll want to use these libraries. They're very good. They're the standard. Everybody who does GPU computing uses these when they want to use matrix and vector operations. So I'm going to talk about CUBLAS and how to use it, and then where CULA comes in. Let's start with CUBLAS. So CUBLAS stands for CUDA Basic Linear Algebra Subroutines. And how many of you have heard of BLAS? You've heard of BLAS, yeah? So BLAS is the library of basic linear algebra subroutines. And BLAS was written in Fortran originally. If for all of you Fortran programmers, you might recognize the word subroutine. That's sort of the word for a function in Fortran, right? Yeah, functions and subroutines in Fortran. Yeah, it's been a while since I programmed in Fortran, so, but yeah, subroutine is a Fortran construct. And hence, well, that's, BLAS is a Fortran library. There's ways to call BLAS from C. If you C programmers know, a lot of people do that still. And CUBLAS is sort of the extension of BLAS for CUDA-C. So just to overview this package a little bit, let's take scalars, alpha and beta, a couple of vectors, and 3 matrices. This whole package is divided into 3 levels of functionality. The first one is a bunch of vector-vector operations. For example, you might take one vector, multiply it by a scalar, and then add on another vector. And there are a bunch of variations on this same theme. That's level 1. So level 2 is vector matrix routines. So you might do vector matrix, multiplication, add on another multiple of a vector, and those are your level 2 functions. Level 3 are all matrix-matrix functions. They're functions of this form and variations on that same theme, and for different kinds of implementations of matrices. So just to overview some level 1 functions, let's define alpha, x, and y as before, and let's let G be some rotation matrix, and let H be some arbitrary 2x2 matrix. Then we have a bunch of functions like this. So given a vector, you can find the index of the maximum, the minimum. You can take the L1 norm. You can take, you can scale vectors, you can add them together. You can copy them, sum them up, take the L2 norm, rotate vectors, do matrix multiplication in 2 dimensions, and you can swap 2 vectors. And those are just this is a sense of what you get in the L1, level 1 functionality. Over here, just for reference, I have a column of sort of the R syntax for all of these things. So there are functions that take floats and doubles as your basic data type. There are also complex and double complex data types that CUBLAS supports. So level 2 functions, there are a bunch of them. I'm going to go over 1 or 2, probably this just one. So there's this basic vector times matrix times a scalar plus a multiple of another vector. So computations of this form are very common, and this is sort of a catch-all thing. And you can take, in this matrix here, you can take either A, or the transpose of A, or the Hermitian, or use a Hermitian operator of A, which is basically the conjugate transpose if you're working in complex numbers. And you pick what version of A you want with this trans A argument in these macros over here on the right side. Now, this function, this basic routine has a bunch of different implementations for the basic float type, the basic double type, and also the complex types. And there are also implementations for different kinds of matrices, because it can take a lot of space to store a matrix, right? So you can use properties of a matrix like symmetry or triangularity or bandedness to sort of compactify the way you store them. And CUBLAS, if you tell CUBLAS, hey, this is a triangular matrix, or hey, this is a symmetric matrix, CUBLAS will take that into account and it'll optimize the algorithm. It'll compute it in an optimal way given that method of storage of the matrix. And so for two functions, you may apply different things based on if the matrix is banded or symmetric or triangular, or if it's stored in packed format. And the storage of the matrix is reflected in these two letters right here. So I guess I should, I'll actually explain that later. No, I can explain that now. So CUBLAS, at the very beginning, that's just the beginning of all CUBLAS functions. This capital letter here determines the data type, so S for float, D for double. And these next two letters are the matrix type. So GE stands for general. And then you have a bunch of different things for different types of matrices. And the last two letters denote the routine. So MV is matrix vector multiply. So you have GMM, which is your more common thing you're going to use for matrix multiply, and that'll be later. So most people, when they think of CUBLAS, they think of CUBLAS SGen. That's for general matrices A, B, and C. They're compatible. You take the product of A and B plus C, you store the result in C. Now, you don't need a plus C. You can just set beta equal to 0 if you feel like it, if you just want to multiply A and B. And again, this op means that you can take the transpose of A, the transpose of B, the transpose of both, multiply, or well, not necessarily both, because A and B have got to be compatible, but you have some flexibility in terms of how you multiply these things together. You also have, if you have arrays of matrices, then you can compute all these products in batch mode. So you take the product of each one. There's that feature. And you can solve systems of linear equations when you have a triangular matrix as well. That's pretty useful. These two functions compute, they solve for x in both of these cases. So the triangular matrix can both be on the left or the right side. All right, so CUBLAS has much, much more. I don't want to bore you by listing all of the functions in CUBLAS, but these are just some of the more useful ones. There are lots of other functions, lots of variations on these functions depending on what the data, how the matrices are, special properties that the matrices have, etc. So let's go right into an example of using CUBLAS. Well, first some tips on using CUBLAS. So before we get to an example, I should say that since CUBLAS is based on BLAS, which is written in Fortran, matrices are stored in or referenced in column major order instead of row major order. So you think it's the right order? Why do you think column major order is the right one?
Because that's the way naturally inside arrays are stored in the
Arrays are stored naturally?
Yeah, it's faster to go to access elements. That's the theory when Fortran did it.
Huh.
Yes.
Arrays in C? Is that?
Sit down and argue about that, but
Well, is that?
that's the way it was. I'm a Fortran guy, so I know.
Well, in Fortran It may be. In C, people who are used to C would say, well, it doesn't quite matter because there are pointers to pointers, right? And the first pointers are stored in an array and they point to different places, but
But then you have to go further to get that.
you do. You do have to go further. We
Vectors as columns and
Right.
matrices, especially columns captured.
That's true. Yep,
So that's how I.
that's true.
Anyway,
All are
that's
yeah.
beside the point because given this, at the time, it is 1976 when impact was, thought of and designed, etc. At that time, things were very much different. I mean, going from here to here was very slow.
Mhm.
So,
Right.
so they tried to implement best way they could.
Okay.
Grab speed wherever they can.
Mhm.
Nowadays, it doesn't really matter.
Mhm. Well, I
Because
didn't.
given the speeds,
Huh. Well, yeah. I appreciate that comment. I didn't know that the choice for column major order was motivated by speed and the natural ordering of.
access wherever.
Huh. Interesting. It's really interesting. I wonder if pointers changed that at all. Because does Fortran how much are pointers?
When C was invented, the guys at AT&T, they were thinking of doing mathematics. They were not even thinking of matrix. They were character manipulation. They are into character manipulation.
Huh.
They are a telephone company. That's what they were doing. And they didn't think of these things. We had multiply two matrices. They never thought of that. That's the basis.
Huh.
That's and everything that they put into C, you can't correct it anymore later. So they went by what they had. Forwage order.
Huh.
That seemed natural to those people who started with that. For me, it's very unnatural. But
Mhm.
I got to it eventually.
Yeah.
When you write the for loops or something, I had to get used to it. Thinking that way, I comes first, J comes first before I. So
Mhm.
that way.
Right. Right. Interesting. Well, we avoid those sorts of problems here because in CUDA, you always want to work, unless you want to give yourself a really hard time in CUDA, whenever possible, always try to work under the hood with with one-dimensional arrays. Even your matrices are going to be stored as one-dimensional arrays because it's far easier to copy memory to and from the GPU and one-dimensional arrays and just reference using an indexing system that you come up with. And this is the sort of indexing system that is, that I think is reasonable. So you have an array A, and you want to represent this as a matrix. And what you might do is you might want to represent a matrix like this with 4 rows and 3 columns, as sort of matrix B. And I want to set up a correspondence between an indexing system where I take the row index and the column index of B. Well, actually, my indexing system goes the other way around. So I want to be able to take an index in this array, A, and know what the right row is and right column is of that element in B. And here's how I do it. So I define a function like this. So the element j time, if I want to go to row I column j of A, here's what I might do. I take j times LD plus I, where LD is called the lead dimension of the matrix. And this is in column major order, not row major order. So LD is the length of a column, equivalently the number of rows. And what you can do now with this indexing system is you can just say, I want to take row I column j, that element of B, I want to know where that element is in A, and it's the j times LD plus ith element that I want to take out of A, and all of the right element at B. And so if you just use this indexing system, you can pass in linear arrays and just pretend that they're matrices. And so I define one strategy that I've seen a lot is just to define a macro at the beginning, something like this, where the preprocessor will sub in this whenever you write this in your code, and you'll be fine. You can put this inside square brackets when you index this linear array. So you'll see that in the examples. There's also something you need to worry about called a CUBLAS context when you're using CUBLA. So for CUBLAS, CUBLAS probably has a really, I don't know what version it's on right now, but when we got CUBLAS for our systems, the CUBLAS is in the middle of transitioning to or out of version 4.0. So versions above 4.0, you need to create something called a CUBLAS context, sort of a bundle of all the handlers that CUBLAS needs to run. So before you do any CUBLAS, you need to create this handle. You need to, well, declare this handle, create it, and then destroy it like this. Notice the ampersand here that's not in CUBLAS create, that's not in CUBLAS destroy. So, and you pass the handle to every CUBLAS function in your code. And what that does is it allows you to use multiple host threads, like POSIX threads, and multiple GPUs. I'm not going to go over that, but that's one thing you can do that this feature allows. There are also these helper functions that you can use, getting vector and setting a vector, and the same thing for matrices. You don't actually need them, but CUBLAS has them available if you want to use them. They're kind of handy for some people sometimes. And then there's this issue of choosing the right API. So there are two APIs. So there's a new version for, well, a newer header and an older header for 4.0 and above and less than 4.0. Know what version you're using and choose the right header. Version 2 for CUBLAS header, version 2 for CUBLAS version 4.0 above, and just CUBLAS.h for lesser versions. So I already talked about CUBLAS create. Little things, scalars can be passed by reference to device functions. You get error statuses, which is really good. My examples are going to use error statuses. You always want to return error statuses from your functions, look at them, and diagnose errors that way. Very important. Otherwise, they go silent, and you're just scratching your head trying to figure out what went wrong in the GPU. So there are these CUDA malloc and CUDA. You might see CUBLAS alloc and CUBLAS free in older CUDA code that uses CUBLAS. You would not want to copy that usage for newer versions. You would want to use CUDA malloc and CUDA free, just in case you see those things. And there's this streaming issue. That's just here for reference. I'm not going to go over streams. So if you have a program with CUBLAS, here's sort of how to compile it. You got to make sure you have one of these headers in your source. You got to have the compiler flag lcublas. So -l means, load this dynamic library or load this shared object. And CUBLAS is, or CUBLAS.so, I believe, is the name of your shared object. And automatically, the compiler automatically looks for that library. So it knows to load those functions. So here's an example. So I just compiled this example 2, which I'm going to show you. There was an example 1, but I decided I didn't like it, and I got rid of it. And I didn't want to rename example 2. So just type in nvcc, lcublas, source, and then your binary. Now, we're going to go into this example right away. I should just say that this matrix is the output. You have this 5-row, 6-column matrix, and it's going to start out as the numbers from 1 to 35, and it's going to fill the matrix with those numbers in column major order like this. But notice these 3 numbers are modified, and these 4 are modified. What the program is going to do is it's going to take the second column, and it's going to take all of these lower entries in that column. It's going to multiply them by 16. And it's going to also take this 3rd row, and it's going to take everything beyond this element in this row, and multiply those numbers by 12. And that's all it's going to do. That should hopefully make that example easier to follow. So, example 2. We're loading the newer CUBLAS. M is the number of columns, N is the number of rows. Here's my column major order indexing function. I have j minus 1 and I minus 1 now because I didn't want to do the minus 1s before in order to keep things simple when I was explaining it. But keep in mind that entry indexes start from 0, so I have to do that minus 1. Here's our modify function, which takes that matrix and multiplies those entries for you. It does this with this function CUBLAS scale, which takes sort of a subset of a vector or an array, and it multiplies a bunch of the entries. So I pass in the handle. Alpha is a scalar. It's the number to multiply by. Here's where to start. You start at entry at PQ at row P, column Q, I believe. And then this last number is the offset. So it's going to multiply. It's going to multiply the number stored here, go LDM places down the array, multiply the next one, go LDM places down the array, and so on. So that's going to hit, that's going to hit a bunch of entries. And then I do the same thing, CUBLAS scale. I'm going to multiply by beta. But this time I'm only going to do offsets of 1. So if one of these goes down a row, the other is going to go down a column, because here my offset is the lead dimension, and here my offset's just 1. Yes?
Can you go through that inline thing first? I missed that.
Oh, the inline? Oh yeah, the static inline. So inline is kind of makes your function behave like a macro. So it just inserts it everywhere. It's a preprocessor's job. There's really there are some subtle differences between inline and define, but you know. And notice, I usually have defined kernels up here. I don't need to define kernels because CUBLAS scale has the only kernels you'll want in this program. So with that in mind, we can get right to it. So I initialize a CUDA, something to catch the errors. I initialize the handle. I allocate some memory. So the dev pointer A is my matrix on the device. I downloaded this program from the documentation of CUBLAS, and it's very good at checking errors. I did not write this code. It even checks the error in malloc. You'll notice the errors in the CPU memory side more easily than in the GPU memory side. It checks, allocates the matrix on the device, creates the handle. Remember, CUBLAS create. It creates that handle to create memory to set the to copy the matrix, the memory stored. Yeah. So you have this CUBLAS set matrix here. You didn't actually need that, but there are ways around it. This code uses it. Actually, where am I? Oh, that's why I forgot to. I was confused because I was wondering, where. So this command copied the host copy of the matrix A to the device copy of the matrix A. At this point, we already have our matrix lowercase a because we filled the entries here. We just go up our list of integers 1 to 35 and fill the columns with them in column major order, and we have them. We copy them over to the GPU with CUBLAS set matrix. You could, yes? Yes.
But in this slide, you use CUDA melloc. So which one is better?
So I have CUBLAS malloc.
Yeah. Before slide. Before slide.
CUBLAS. I have CUDA malloc here. Where do you see CUBLAS malloc?
No.
Oh.
You can use both. But
You can use both. Oh, okay. I thought you said you saw it in here. Okay, and I was looking for it, but yeah, it's just one of those things where NVIDIA's getting away from the use of that function, and it's in future versions I expect it to just not exist anymore. CUBLAS malloc. Yeah. They're just. I think it's just a design preference that they're getting away from CUBLAS malloc. I don't actually know, or CUBLAS alloc I should say. But yeah, I don't exactly know why, but they're doing it, and if it eventually it's just not going to exist anymore. And CUDA malloc does the job, and you're going to be using CUDA malloc anyway, so I'm sure that when it's basically the same thing. Yeah. I think CUBLAS alloc might have taken into consideration, things that are handler now did. Remember CUBLAS create handle? I'm not sure, but CUBLAS alloc might have taken care of those same issues that CUBLAS create takes care of currently. I don't know that for sure though. That's just my speculation. Anyway, so we did all this work and all this error checking to set things up. All these if statements are cumbersome. I downloaded this code from the documentation and didn't modify it, but it's easier to do what I'm going to do in the next example, which is just to wrap everything in a macro that checks errors for you. Right. So we have our matrix on the device, and we call modify, and we're going to call it on we're going to pass in the handle because we're going to need it for a CUBLAS S scale. We're going to pass in the matrix on the device. We're going to start at row 2, column 3. We're going to multiply all. So this is our alpha from before. We're going to multiply those column elements, those second column elements by 16, and all the third column elements by 16, second row elements by 12. And our result should be in dev pointer A. Now get matrix writes everything back to the CPU side. So I pass in our dev pointer A, we're copying it back to A, and we're passing a bunch of other parameters that help with that copying. Of course, we do some error checking. We do CUDA free on our dev pointer when we're done. Remember to destroy the handle, CUBLAS destroy, and we print out our matrix. And just to remind you, this is the output. All right, I'm going to go.
Can you stop at the top of the program?
Yes.
Yeah, next page. Okay,
Here?
just hold it.
Right. Ready to move on? Yeah? Let's do more.
In reality, that part, the modify is a major part, right? All the other things are setting up stuff.
Right, right.
There's this little thing that you're doing.
Exactly.
It's all this other stuff.
Exactly. I mean, programming in CUDA, it's kind of annoying like that because there is so much setup, and what you actually want to do is just this tiny little bit. Anyway, let's go to a more statistical example. So I'm going to attempt to solve the first regression problem you ever taught, ordinary least squares. And I'm going to do it with matrix algebra. I'm going to compute the UMVUE, the beta hat of beta in this least squares problem. I don't know why my pointer stopped working here. Oh, there we go. Having all sorts of trouble today. Anyway, so here's our model, simple as we can get. I don't need to specify a distribution on epsilon because we're not doing inference. All I want to do is just solve for that estimator. Is just solve for that estimate, beta hat, with this quantity here. We learned in the first stat course that used matrix algebra that we ever took. So x is our design matrix, and y is our vector of observations. We want a vector of parameter estimates out of it. So I'm going to use CUBLAS and see if I can get as far as I can. So here's our error wrapper for error checking. Here is our column major order indexing system, indexing macro. Our norm is just the Box-Muller transformation. That's just so I can generate responses. I can generate the y's. I begin here. So I initialize a bunch of things. IPIV we're going to need much later, not now. So I have matrices, but I do initialize linear arrays of floats for what are going to be the matrices x, x transpose x, and x transpose y, and beta, and our response is y. And I initialize all the same things on the device.
I thought the R norm was implemented already.
It is, and curand. And it probably is in GSL as well. But this is really simple to write too. You know, I mean, both are just as easy. But I'm sure our norm is definitely out there, and I could have just used that. It would have probably been better too, because you know, this is kind of a waste only using one part of the Box-Muller transformation here. Anyway, so I set up a bunch of stuff. Here I'm allocating memory, and I'm wrapping all the memory allocations in CUDA call to check errors. This is much more compact than the previous example, because I have this CUDA call macro to check errors. It makes things much nicer and neater than otherwise. Remember, also, I have my handle. And here what I'm doing is I'm initializing, I'm giving values to the design matrix. So this is going to have 3 columns. First column is just a column of ones, that's the intercept column. The second column is a sequence of numbers you know, that form a line. The third is a sequence of numbers that follow a quadratic term. So this is a regression on, this is a regression on a parabola. And I just use some quadratic plus a normally distributed offset to initialize my random responses y.
This might be slightly off topic, so cut me off. But if I just had data and I wanted to get it into this program and not have my program generate the data, how would I go about doing that?
You couldn't just get data into this program. I wrote it and hard-coded the data just for pedagogical reasons. This program is purely pedagogical. It's not actually a full-fledged regression program. So you couldn't do it here, but you could easily write something where it just reads from a file. Yeah, sometimes writing the code to read a file and read it cleanly is less understandable and on slides in presentation than something like this. And then I print them out just to show you what they are. I copy x and y to the device. And I call CUBLAS sgen, that's the general matrix multiplier, to multiply x transpose, that's what this CUBLAS x op does, CUBLAS op t does, multiplies x transpose times x, stores that result in my device copy of x transpose x. That's the first step. And I copy this back to the device back to the host, sorry, so we can print it off and read what it is. All this is doing is printing it. So I have X transpose X, right? Here are my Y's. Here's my design matrix X, and here's X transpose X, right here. Now I need to invert that matrix, right? Because beta hat is X transpose X inverse, or generalized inverse, if you will, X transpose Y. But the problem is that in order to compute this X transpose X inverse, I need this thing to be a triangular matrix. And it's only triangular if the whole thing is 0 because X transpose X is symmetric. So in general, this is not going to be triangular. And so you can't use CUBLAS for this. What you need to do at this point is use CULA. Remember, that's the second library I'm going to go over today. So that's CULA stands for CUDA LAPACK. The LAPACK is something that's built on top of BLAS, also in Fortran, that has a bunch of other great linear algebra subroutines. And I'll get into those a bit later, but it has inversion, and it has a way to invert generalize, general matrices. So after I call CULA initialize, which I need to do before I do anything in CULA, what I'm going to do is I'm going to first call this function. So getRF is an LU factorization, and it's going to take the LU factorization of X transpose X and store the pivots in that factorization algorithm as ints in this array IPIV. And then I'm going to use those pivots to actually take the inverse of this matrix with getRI. So getRI will take the inverse of X transpose X, but I need those pivots from the LU factorization. But I've got my inverse now, and relatively fast. Once I've got it, I copy it back. I print it out just to as a checkpoint for the user. I didn't actually need to print it out, but it's nice. I have X transpose X inverse, but I also need X transpose Y, and that's a simple call to CUBLAS. That's a simple call to SGEM again. If we think of Y as a matrix and not really it is just one column, we can call the vector Y actually a column matrix. And I can do this multiplication stored in X transpose Y. I could have done SGEM V as well if I wanted to consider Y as a vector. But I did SGEM because I like SGEM. And it takes X transpose Y, stores that result. X transpose Y is a vector, so I could also use SGEM V for my next multiplication, which I did here, to take X transpose X inverse, which is stored here, times X transpose Y. And I store the result in beta because those are my final answers, or D beta rather. I copy back to the host, I print out my betas, and I'm done. But I want to do one more thing, because there's this function called sgels. And sgels is really convenient because what that does is it does all the previous work that I did in one line. So CULA sgels is a built-in ordinary least square solver. So I could have avoided all that work, but I chose to do everything the hard way before I did it the easy way. So it just takes, it says do ordinary least squares at design matrix X and responses Y. Now I print out those betas. Now I call CULA shutdown, because CULA initialize and CULA shutdown have got to allocate and free everything you need for the handle. For the handlers of CULA, I free my CUBLAS handle, I destroy that, and then I free everything else with free and CUDA free. And here's our output. So we have our X transpose X inverse that we got from CULA. There should be parentheses around X transpose X. That's all inverted. So these parameter estimates from CUBLAS and CULA, from all the matrix algebra, these are the parameter estimates the hard way, and they agree with the estimates from the easy way using CULA sgels. there might have actually been differences there because of differences, differences in calculations always lead to differences in rounding error. So they're going to be just as scientifically valid, but yes, there will be rounding error.
The X transpose X inverse, all that kind of stuff. It's good when you're doing linear algebra by hand, but when you're actually implementing it on a computer, you don't actually code that way. Don't you use like SVD, all that?
You do. Yeah, you use SVD a lot.
Right, it's more numerically stable and such. So
Yeah.
I would expect these numbers to actually be different.
Yeah. They should be different. So they're different algorithms. SVD is used in practice. So I mean, not significantly, obviously, but you wouldn't get the exact same numbers.
I was also thinking if you knew how to use this API, it doesn't seem like you need to know very much about the hardware.
You don't need to know much about the hardware. That's the nice thing about these things, is they take care of a lot of the hardware issues for you. They take care of kernels and allocating, dividing things up into blocks and threads. All that parallelism is taken care of for you. You do, though, have to, for most cases, have to know how to copy stuff to and from the GPU. Was there a question? Redundant functions. I think there are a few. That's a good question, and I think I have some in my slides later. Yeah, there should be some redundant. I think there are some redundant functions. I'm going to get to that right now. So CULA, let's get into CULA in general. So it's LAPACK for the GPU. So relative to CUBLAS, CUBLAS gives you just rote vector and matrix routines. This does more advanced stuff. So it gives you the LU, QR, RQ, QL, SVD, Cholesky factorizations, all for free. CUBLAS doesn't do that. It solves systems of linear equations for general matrices. CUBLAS only does triangular matrices for that. It has a least squares solver, and it has a bunch of eigenvalue solvers as well. Those are the main components of CULA, and CUBLAS does not have any of these last four. It does, the matrix algebra routines, some of them are a bit different though. The important thing about CULA is it black boxes things a little more. So it has two different kinds of interfaces. There's a standard interface where you don't even need to worry about copying things to and from the GPU. So you give it an object in memory on the CPU, and it'll copy it there for you, do the routine, and write it back for you, without you having to call CUDA free or CUDA malloc at the end or beginning. You don't need to worry about that stuff if you use a standard interface. There's a device interface, which I used, where you need to explicitly allocate GPU memory and do the copy yourself. So they work directly on the device, on things in device memory, rather. So if you're using the standard API, standard functions, you give it things that are stored on the host. If you use the device API, you give it things stored on the device. Be careful, though, because what if you're doing multiple computations on the same object, and you use a standard interface? Every time you call something in the standard interface, there's this expensive write and this expensive read back. So unless you're doing a single computation with CULA per object that you want, you're better off using the device interface, because if you're copying things multiple times, the program gets slow. Remember that bottleneck? Copying memory from the GPU to the CPU and vice versa? That connection is very poor or very slow. All right, naming conventions. Just mostly like, this is very similar to CUBLAS. There's a prefix that tells you, it tells you, what library you're using. This is CULA. There's a basic data type. This is capital letter, matrix type, and routine. So there are a bunch of matrix types here for reference. I'm not going to go over these. but they're there for your reference. The slides are going to be online. There are a bunch of routines that you can use. There are a bunch of, these are mostly factorizations. So compiling with CULA, when you compile with CULA, you need the header file that corresponds to the interface that you're using. One of these, CUDA-LAPACK, is for the standard interface. There's another one for the device interface, but I like to load just CULA.h so you get both interfaces. They don't conflict because the functions in the standard interface are named slightly differently in their prefixes than the other ones. So you might compile like this. This -I and -L flags are just to say, you know, look for my header files, my .h files here. After the -L flag, I'm saying look for my shared objects in here, my libraries. And then I'm going to load CULA core. You need that to run CULA. CUDA-LAPACK, you need that to you need that to run CULA as well. Here's CUBLAS, and CUDA-RT is the CUDA runtime library, and you'll need that for some things that you do. I think NVCC might actually automatically load this, but I'm not sure in some cases. And these comments are available for your reference. I already explained them. So here's a minimal working example with CULA. You just get a CULA status to check your errors with, and then you call CULA initialize, and then you check that error, you run your code, and then you call CULA shutdown. And it's meant to be, and it's really that simple. So all of this CUDA malloc business would have taken, you know, 10 or 20 lines instead of this line 8 CULA initialize, plus, you know, all your other CULA functions, really. I mean, this compactifies and eases a lot of the burden.
You can use that method even if you have, you know, multiple threads.
It does the parallelism for you, actually. So you would, parallelism on top of what CULA has already would require CPU threads or multiple GPUs and or streams, which are, I'm not going to cover this, but if you want, so the parallelism happens inside CULA.
Oh.
Yeah?
So you mean we don't need to care about some block or grid?
You don't need to work with blocks and threads at all if you use CUBLAS and CULA. So you don't need to make any kernels. These libraries make all the kernels for you. And all the kernels, all the parallelism is embedded inside these libraries. I should have said that at the very beginning, because these libraries take care of all this parallelism for you and make your life a lot easier than otherwise.
So that means if you're doing a million by million matrix, if you're doing, you know, inversion or something.
Right.
Just put it in, right?
Just put it in. Exactly. Yeah. Yeah.
I use it today.
Yeah. Wait till we get to thrust. It makes that library makes things even easier than this. That's why so many people use CUBLAS and CULA. Unfortunately, CULA costs money. It's not free with your CUDA installation. But the good news is we have CULA on our Impact servers.
Do you know the price?
I don't know off the top of my head. I would ask Dr. Nimi or the IT guys. I think they would know. I don't remember. Anyway, here's an example compilation and run of the minimal working example that's there for your reference. Here's what we went over. We went over CUBLAS, CULA, parallelism black boxed completely for linear algebra stuff. So there are some guides online. You can search these things on the internet and you'll come up with PDFs that NVIDIA posts that are great, that are documentation for all the specific features, because some of these functions, especially in CUBLAS, have really long lists of arguments, and you need to go through each one and make sure you have the right one. I can never remember the argument lists off the top of my head. I've got to look up, these 10 or 15 arguments that you pass in.
LAPACK itself
Yes.
that problem.
Yes. Yeah, LAPACK has those same long argument lists. And I should say that this documentation, although pretty good, it's when you first look at it and you haven't had experience with LAPACK or BLAS, it seems inadequate because these assume knowledge of LAPACK and BLAS. So for any unanswered questions, you might want to look at the LAPACK and BLAS documentation before you read this. And there are 3 code files from today. I think ols.cu is the most pedagogically informative one. So if you're looking for basic familiarity with those things, that might be one to use. And I have other example code online for both of these libraries, and you can check it out. It's all on the website. And thank you for your time.